Hey guys, this is Hemant from Edureka. Today's session is going to be on logistic regression. So without wasting any more time, let's move on to today's agenda to understand what all will be covered in today's session. So we'll start off today's session by discussing the 5 main questions which can be asked to you in data science. Now based on these questions, you decide which algorithm to use, right? So we'll see how regression fits into these questions, and then we'll move on to the part where we'll be discussing what regression is exactly. After that, we'll move on to the topic of the day, which is logistic regression, and then we'll understand the what and why of logistic regression. After that, we'll see how logistic regression actually works, and towards the end, we'll be doing a demo wherein we'll be taking the diabetes dataset and we'll be solving the dataset using logistic regression. In the end, we'll be discussing the use cases as in the real life scenarios wherein logistic regression is actually used. Alright, so guys, this is our agenda for today. Are we clear with it? Alright, I'm getting confirmations. So Dinesh says yes. Others, Pallavi, Bharat, Karan. Okay guys, so I'm getting confirmations from you all. Alright, so let's start with today's session. So our first topic for today is the 5 questions, the only 5 questions which can be asked to you in data science, and based on these questions you decide which algorithm to use. Right, so the 5 questions which can be asked to you are this. The first question that it could be asked is this A or B? Is this an apple or is this a pineapple? Is this a pen or is it a pencil? Is it a mouse or is it an elephant? So when you have these kind of questions, the algorithms with these kind of questions is the classification algorithm. All right. Our next question is this weird? All right. So basically this question deals with patterns. So whenever there is a change in pattern, the algorithm detects that. And the algorithms which deal with these kind of problems are called anomaly detection algorithms. Then you have questions which are quantifiable, wherein you ask numbers, how much or how many, right? For example, what will be the temperature for tomorrow? Or after how many days it will rain? Right? So all these kind of questions are tackled by algorithms which are called regression algorithms. Then you have questions like how is this organized, right? So basically these deals with clustering, and the algorithms which deals with these kind of problems are called clustering algorithms. Then you have questions as in what should I do next, right? So if you don't know, when you have to make a decision, so taking capabilities uh, are basically done by algorithms which are called reinforcement learning. So using these algorithms, you can take a decision as in what to do next, right? So these are the 5 questions which are asked in data science, and these are the algorithms which are made to tackle these kind of questions. Now our topic for today is logistic regression. So as the name suggests, it comes under regression algorithms. But with logistic regression, this is a scene that the answer which comes is categorical, as in the answer is either a yes or a no, or it's either A, B or C, or it's either true or false, right? So it is classified, the values are fixed, the values are categorical, the dependent variable, the output that we are getting is like this, right? So it is also categorized under the classification algorithms as well. So it is a regression algorithm because before classifying the output, you get a probability, and based on that probability, you decide whether it will be a yes or a no, or whether it will be an A or a B. All right, so that is the reason it is categorized under both of these algorithms. Moving on, let's first understand what is regression, right? So what is regression? So regression is basically trying to establish a relationship between two variables. So what happens in this scenario is you have an independent variable and you have a dependent variable. So the dependent variable is related to the independent variable. So like in our case, y is dependent variable and x is the independent variable. So as you can see in the graph, as the value of x increases, y also increases. But y value is dependent on x. X can increase as much as it wants, but y will increase according to x, right? So y is dependent on x. So now where does regression comes into the picture is, for say an arbitrary or a random value of x, what will be the value of y? So you're predicting y, correct? And this prediction is done using regression algorithms, and that is what regression is all about. All right. So any doubts regarding to what I've told you guys till now, as in what is regression? So it is basically estimating a relationship between a dependent variable and an independent variable. All right. So guys, are we clear with what is regression? Okay. So Karan saying yes. Okay guys, let's try to make this session as interactive as possible, because then it will be in the benefit of both of us. Alright guys, so since most of you are clear, let's move on to the next topic. We have discussed what is regression, and regression is basically categorized into three subparts, right? So there are basically three types of regression. So the first type of regression is the linear regression, then you have the logistic regression, and then you have the polynomial regression. Today we are going to discuss about logistic regression, right? So let's move on to the part where we'll be understanding what a logistic regression is. But before that, let's understand where do we use logistic regression, or why is a logistic regression actually needed, right? So why logistic regression? So whenever the outcome of the dependent variable is categorical or is discrete, so when I say discrete, it means the value is fixed. Can either be an A or a B. It can either be a 0 or it can be a 1. So if I'm asking you a question like, is this animal a rat or an elephant? So you cannot say it's a dog, because my question is this a rat or an elephant? Are you getting me? Alright, so when you have these kind of possibilities, when you have outcomes which are discrete, which are categorical, as in which are predefined, you use logistic regression. Alright, so now my next question which can be asked is, why can't we fix the formula of linear regression in this? Right? So let's understand why can't we use linear regression. So guys, this is the best fit line that you get in linear regression. So if you guys know about linear regression, we have already discussed what a linear regression is. But for the people who don't know about linear regression, let me give you a quick summary. You use linear regression when you have the y value in range, right? But in our case, our value is discrete, as in the value could either be 0 or it could be 1. So as you can see, these are the values for our y. So our y could either be 0 or be 1. But the best fit line for a linear regression is this, right? And as you can see, it is crossing 1 and is also going below 0. But our y value cannot be below 0 or above 1, right? It could either be 0 or be 1. If we were to clip the line, so the only solution that we can see over here is that we have to clip the lines of this best fit line, right? So when we clip the line, it comes out to be like this. So this had to be solved, because this is nothing. This kind of curve cannot be formulated. This is actually not a curve. These are basically three straight lines, right? So this had to be formulated into an equation. So once it's formulated into an equation, it comes out to be like this. So this is a sigmoid curve, right? So it's a sigmoid function curve. And it is basically very famous. It's called the S curve. Now we had to make an equation which will make a curve, or which will come out to be like this, all right? But why this is the question. So let me address that. So as you can see, a value of y is 0 for certain values of x. And our value is 1 for certain values of x as well, right? Now this is the transition that is happening, right? So after 4, the values are becoming 1, right? The y value is becoming 1, right? So this transition has to be represented by a curve, and hence we came up with this S curve. Now in logistic regression, how do we decide whether the value will be a 1 or a 0 when we are predicting it through a model? So logistic regression basically gives us a probability, right? So it will tell me what are the chances of y being 1. So for example, we have a match going on, right? And we want to predict which team will win. So if my team has scored 75 runs and I ask my logistic regression model, tell me whether this team will win or not, right? So with 75 runs, it calculates its probability of winning through the values that we would have trained the model with. And it calculates, okay, the winning probability of your model is 0.8, right? This is the winning probability. Now we have to decide what will be the threshold value, what will be the value above which we will definitely win, all right? So we define, okay, so if my probability comes above say 0.5, if my value comes above 0.5, my probability, whatever that probability is above 0.5, let convert it into 1. Alright? So if my team has a probability of 0.8, it is going to win. So if I ask my model, okay, my team has scored 75 runs. So what my model will do is it will calculate the probability of its winning, which is 0.8, and then it will apply the function, or it will apply the if-else model, as in if 0.8 is greater than 0.5, y is equal to 1. If yes, otherwise it will be equal to 0. Alright, so this is how logistic regression actually works. Now this is how you predict values through the S-curve. Right? So basically we had to come up with this kind of curve because this is the curve which will represent a logistic regression because of the transformation which is happening, right? So having this kind of curve, we should have a linear equation, right? So for coming up with the linear equation, we compared our linear equation to the straight lines linear equation, which is like this, right? Now in this, our y's range, which in the case of straight line, our y's range is between minus infinity to infinity. And if we talk about logistic regression, we get probabilities and a y's value is between 0 and 1, right? So we had to change that. We had to change the range of our y so that this equation can be achieved, right? So in this, basically this part will remain the same. The y will change and hence we can come up with a linear equation which will represent that curve, all right? So our y's range for now is between 0 and 1. So we had to change the value of y. So if you want to make our value between 0 and infinity, what we can do is we can divide it by 1 minus y. If we do that, if y is 0, it will be 0 over 1 minus 0, which is 0. And if y is 1, it will be 0 over 1 minus 1, which is 1 by 0, which is infinity. Right? So my y's range has now become between 0 and infinity. But we want our y's range between minus infinity to infinity, and hence we do one more transformation and we apply the log function to it. So log of 0 is minus of infinity and log of infinity is again infinity, right? So now this function, this particular element, that is log of y over 1 minus y, has a range between minus infinity and infinity, and hence it can be compared now with this y whose range is between minus infinity and infinity, and hence it becomes a linear equation. So this is the linear equation for this S curve. Alright, so guys, any doubt in whatever we did? So Karan is asking me, is this formula used in our logistic regression R? No, Karan, so while you're working with R, you will not be implementing this formula. This is the formula which happens in the background. The reason I'm telling you this formula is because whenever you're passing a command, you should know what that command is actually doing. You should understand the maths behind it, right? So this is the maths. Exactly. Okay, so any more question, guys? Anything that you didn't understand in this part? Okay, so you guys are giving me a go. Let's move ahead then, guys. So we have understood why logistic regression is actually used. Now let's move on to the what part. The what is logistic regression? So logistic regression or logit regression or logit models. So logistic regression is also known by these names as well, logit regression and logit model. So it's a regression model where the dependent variable is categorical. So whenever, like I've been saying in the previous slides as well, whenever the dependent variable is categorical, you use logistic regression, and that is what it all about is. What happens in logistic regression is you calculate probabilities as to what is the probability of y being 1, and based on those probabilities you take a call what will be a threshold, and whenever your value is above that threshold you convert it to be a 1, and whenever your value is below that threshold, your probability value is below that threshold, you calculate it to be a 0. Alright, so this is what logistic regression is. Alright, so categorical is when your values are fixed, they are discrete. Your values could be either A or B or C, right? Dependent is when your Y is dependent on X, right? So X value is independent. You can fit any value in the X, but your Y value will be dependent on X, and whatever input you give to X, Y will change according to X. Y cannot have its own value. Y will always have a value according to X. Whatever relationship it shares with X, According to that relationship, it will take a value, right? So y is dependent on x. So whenever our dependent variable is categorical, we use logistic regression, and this is what logistic regression is all about. You have seen the graph, guys. This is for your understanding. Let's see the graph again. So this is our y value. This is my value of y. So it's between 0 and 1, right? And my graph is like an S curve. So my values are transforming from this point till this point, and this is the best curve that can be fit according to my model. Now in between this, my logistic regression model will come up with values. So for say this x, it comes up for this value. So let me draw it for you. So if I give my model this value of x, right? So my model will calculate which value on the graph is my x pointing to, right? So if my model will calculate this value and we'll see this value corresponds to what value of y, right? And this value is actually the probability, right? So this value is basically the probability. And when this probability is converted, whenever you get this probability, based on this probability, you decide whether your y will be a 1 or will it be a 0. And how is that calculated? You decide a threshold, and based on this threshold, your model decides whether it will categorize it under 1 or it will categorize it under 0, right? So this is what happens in your logistic regression model. Now, how does it work? So let me give you an example. We have understood the theory that this is the way it happens. So let's see it in a real life use case. So I have a list of people's IQ, right? So I'm a company and I want to recruit people, all right? So I came up with their IQs. I have their IQs in my hand and I want them to be selected automatically using a logistic regression model. Now we have not discussed yet what a logistic regression model is. So let us consider this to be a black box. Okay, so we don't know what is there in this model. What we will be doing is we will be feeding these values to the model, all right? And a model will predict whether this candidate will be selected or not selected based on his IQ. All right, so for example, 147 IQ has been selected and 107 IQ has not been selected, right? So it is a calculation which is done in the model. So basically what would have happened in the model is it would have calculated its probability of being selected based on my past records, and it would have compared it with the threshold, and if it was less than the threshold, it would have categorized it under the not selected part. If it was greater than the threshold, it would have categorized under the selected part. So this is how it happens, guys. We now know what logistic regression will actually do. We have an abstract understanding how logistic regression function works. But what we don't know is the main part, that how is this model created? How do we come up with this model? All right, so now we'll be discussing how can you create this kind of model in logistic regression. All right, so let's take an example and let's take a sample data set which is inbuilt in the R Studio language, which is empty cars. All right, so you have these many values. Don't get afraid with the values that you're seeing. All right, these are just values. It will be clear to you in a minute. So you have these values. You have MPG, CYL, DISP, etc. And the focus should be here, VS and AM. So as you can see, the values of VS and AM are discrete or are categorical. They are either 0 or a 1, right? So what we'll be doing in our exercise today or in this example is we will be predicting based on these values what will be the type of engine of my car. Will it be a VS engine or will it be a straight engine? So if the value of my VS engine is 0, alright, so that means that car will not have a VS engine, hence it will have a AM engine or the straight engine. If my value of VS is 1, that means my car will have a VS kind of engine. And these values will be calculated based on these inputs. So these are actually the parameters of the car, MPG, and you can actually look at what this means in the key for the data set. So MPG basically means miles per US gallon. Your CYL is the number of cylinders in your engine. Your DISP is actually the displacement, right? Your HP is the horsepower, the gross horsepower of the car. Your DRAT is the rear axle ratio, etc. Right? So WT is the weight. Now, what we'll be doing is we'll not be taking all the values. Now, this is a step that you will be learning in the demo part of today's session. That how do you select which values to take in this model? So as of now, forget how we select values. We will be selecting DISP and WT. Alright, so while we are creating a model, we'll be feeding in only these two values out of the whole model, and we'll be predicting Y. What is Y? Y is basically VS. Alright, so we'll be predicting VS based on these two values that we'll be feeding into the model. Right, so DISP is basically the displacement of the car, and WT is the weight of the car. So based on displacement and weight of the car, we will predict whether our car will have a VS engine or a straight engine. Now let's see how will we do that. So first, before creating a model, the first step is to divide our data set into training and testing. Why are we doing that? We divide a data set into training because this is the data set that we'll be feeding to the model. This is how we will train our model, right? So our model has to be trained for predicting values. Now, like I told you guys in the starting of today's session, regression means establishing a relationship between two variables. Now, how does it establishes relationship is by looking at the past results or looking at the past records, what has happened before, right? So in our training data set, you'll see like in the Mazda RX-4 car, when the displacement of the car was 160 and the weight of the car was 2.620, type of engine which was used was straight engine, that is VS being 0, so it is straight engine. However, when my displacement of the car was 108 and my weight of the car was 2.320, the type of engine used in the car was a V engine or a VS engine, right? So this is how it establishes relationships. So we will be training our model using the training data set, and once our model is created, once a model is made, we will test that model using the testing data set. Alright, so this is what we do. We divide our data set between two. Now the larger part of the data set will be used in training and the smaller part will be used in the model validation so that we can come up with an accuracy. Alright, so we will be dividing our data set, and then this, like I said, this data set will be used to create the model. So once your model is created, this is what you get when you look for summary of the model. Alright, so when you type in summary model, you will get all these values. Now these values are very important, guys. So this is the value that you need to focus on as of now. So the first value is the intercept. So this is basically the constant value in your equation. Remember, in our estimated regression equation, our formula was logit of y equal to beta naught plus x1 beta 1 plus x2 beta 2 plus x3 beta 3 and so on, right? So over here, our beta naught will be the constant value. Our beta 1, that is the WT is the independent variable that we have fed to our model. Alright, so the coefficient for that is 1.094, that is beta 1. DISP is the coefficient for the model which is beta 2, that is minus of 0.02529. Alright, now these values are calculated by R using the MLE method. What is MLE? It is maximum likelihood estimation. But if we were to discuss how are these values calculated, it is very complex and I can explain it to you guys, but it will take a lot of time. So what you can do is you can Google MLE, right? If you don't understand, you can ping me and I'll explain it to you in the next session. All right? If you want to learn, because MLE would not concern you, these values are actually calculated automatically. That is why we have R to calculate these values for. But if you're still curious as to how these values are calculated, you can Google it, and if you don't understand it, I will explain it to you in the next session. All right? Having said that, okay, so we get these three values, and these three values are actually the coefficients of the independent variables. Next, these coefficients are actually fed into this expression. Now, how did we come up with this expression? When we solve log of y over 1 minus y, which was equal to beta naught plus beta 1 x1 plus beta 2 x2, when we remove the log and if you want to find y, we come up with this expression. So this is basically something like this, equal to y is equal to this, right? So now with this expression, basically you get the probability of y being 1. Alright. Now over here you'll be feeding in the values that are beta naught, beta 1, beta 2, x1, x2, e. E is the Euler's number, which is a constant, that is 2.71, right? And beta naught is the value that you got from here. This is the beta naught value. You have the beta 1 value, you have the beta 2 value, and then you will be feeding the x1 value, the x2 value, and hence calculating the probability. Now again, this is actually in the background. For getting the y value, you simply have to type in predict. You have to type in your data, which is you have to type in x1 and you have to type in x2, and it will automatically implement it in this formula. It will get the beta 1, beta 2 values from the model, and it will predict the value for you. But you should understand what is happening in the background, and that is the reason we have explained you this expression. So this is the expression which is used, which is logit of y is used to calculate the probability of y. Alright? Now, as you can see, these are the values that we got from our data set, right? Now, these are the values that we'll be feeding to our logit y function, alright? Now, where did we get the x1 and x2 from? We took a value from the training data set, and the DISP value is 120.3 and the WT value is 2.140, right? So we'll be feeding these values into the function with the beta naught, beta 1, beta 2 and the E values, and we come up with the value which is 0.4962. Alright, so this is the probability of y. Now as you can see in the data set, if the displacement was 120.3 and the weight was 2.2140, our VS engine value was 0. Alright, so when we are solving it in the equation form, y is basically the value of VS. Alright, so this probability is basically the probability of VS being 1. Alright, so the probability in the case when my DISP and my WT values were this, my probability of y being 1 or VS being 1 is this, right? Now our threshold in this case or in any case is 0.5. Now usually in our probability, we apply the threshold as 0.5. So if my probability is greater than 0.5, we say it's a success. And if we say it's lesser than 0.5, we say it's a fail. So this value is actually lesser than 0.5, right? So if it's lesser than 0.5, then it turns out to be 0. And that is the predicted value of VS, right? So the predicted value of VS from our calculations is 0. And if we compare it with the testing data set with the values 120.3 and 2.140, the value of VS was again 0 over here. Alright, so as you can see, our model was correct. Our model has predicted the right value. Alright, so our model is validated now. So it has predicted the right value for the value of DISP and WT. So this is what happens in logistic regression. Now we have done it manually, as in we have applied the formula manually and we came up with this number. But had it been an R, we would have simply typed in the predict command, entered the WT and the DISP values, and would have came up with this number, right? And then we would have applied a threshold onto this number, whether this number is greater than 0.5 or not. And since it is not greater than 0.5, it would have automatically reduced that value to be 0. And hence it would have matched with the VS value. Alright guys, so this is how a logistic regression function works, right? So this is how it happens. So let's move on to the demo part now. So now we'll be using a different data set, a more complex and a more elaborate data set. So now we'll be predicting, our aim is to predict whether a patient is diabetic or not. Alright, now how will we predict that? We have a data set wherein we have values like these. So we have NPreg, which is the number of pregnancies that that patient has had. We have GLU, which is the plasma glucose concentration. We have the BP, we have the BP levels of that patient. The skin, that is the triceps skin fold thickness. This is the test which is done, right? We have the body mass index of the patient. We have the pedigree per function, we have the age, and in the end we have the type. All right, so we have this data set wherein if these are the values, the type is 1, meaning the patient is diabetic. All right, so he is in the diabetic type. So if the value is 1, it means our patient is diabetic. If the value is 0, that means our patient is not diabetic. All right, so we have to predict by entering these values. We have to create a model which will predict whether our patient will be diabetic or not. All right, having said that, let's move on. So let's create this model now. So in R, first we'll be passing this command. So first we would have to import our data set, right? So let me quickly go to my R console. Alright, so let's feed in this command and see what we get. So first we'll be passing in this command and we'll be including our data set in our environment. Alright, so I've passed this command and this is my data set, as you can see. Alright, so this is my data set, guys. Now our next step is to split our database into testing and training, alright, in the ratio 8:2. Now let's do that. So basically there is a library which first has to be implemented, right? So we will include this library. Why is this library used? This library is used for the split function which is there, right? So for splitting our data set into training and testing, we have to include this library, which is CA tools. Once we do that, we will be splitting our data set into training and testing. Alright, so that has been done. Let me explain you the commands. Alright, so first my data is split. Alright, so this is the data that I've got from the CSV file in this variable. Alright, so this is that variable. Now I'll be splitting this variable in the ratio 0.8. Alright, so what this command will do is it will split my data set or my data variable in the ratio 0.8 and 0.2. So it will be splitting it in this variable, right? So when I'll be passing this variable, what it will do is in the 0.8 part of the data set, the value will become true. And this values, they are picked actually randomly. It's not sequential. Random values are picked and each value is assigned a value which is like true or false. All right. So 0.8 part of my data set will be assigned the true value and 0.2 part of my data set will be assigned a false value. Now what that means is you'll understand in the next line. So once I've said split, the next line is training. For my training data set, I'm saying the subset of data where the split value is true, all right? So where the 0.8 part of my data, which is true, I have assigned it to the training variable, which is the training data set. Then I say for the testing data set, the subset of data in which the split is equal to false. That means the data set which has been labeled as false will be coming under the testing data set. That is the 0.2 part of my data set. All right. So this is how my splitting of the data set happens. Okay, so once I have divided my data set, the next step is creating the model. So let's do that using this command. All right. So my GLM is basically used for creating a model in logistic regression. All right. This part specifies the formula that I'm applying. All right. So my type is the Y that I want to predict. All right. This tilt symbol is basically the versus part. So Y versus X, right? On the X part, I've specified dot. So dot means you have to take into account all the variables right now. So type tilt dot is the formula, comma training is the data set that we'll be using. So we have split the data set like this in the 8:2 manner, right? So we want the training data set and then our family of Y is binomial. So binomial means basically it can take on only two values, that is yes or no, true or false, or 1 or 0. All right, so we have to specify that as well. So let's pass this command now into R and see what will be our model. Right, so let us pass it. So this is our model. Let's run it. And then we will get the summary of the model. Now, what is the summary of the model? The summary of the model is basically something like this. So whatever value will be calculated, that value will be shown over here. So let's calculate the value. All right, so this is the value that you get when you look for summary of the model. All right, so you get a lot of values here. Don't worry, I'll be explaining you guys everything. So basically these are estimate is basically the values of your coefficient, right? So the beta naught, beta 1, b2 that you saw in the previous example is this. So you have a lot of independent variables here and hence a lot of coefficients, right? So these are the coefficients and these will be used when you'll be predicting your value. So you don't have to worry about these values. These values will be automatically taken. The next thing that you should be focusing on here is this. All right, so this is the significance code that your R provides you with. So basically this tells you how much significant that particular independent variable is. So in our summary we have got these significant codes, right? So these significant codes specify how much significant your data is. Alright, so let's see what does these actually mean. Alright, so 3 stars or 3 asterisks, if they have been specified in front of your independent variable, it means that your model is 99.9% confident that your specific independent variable or value is significant to the model. It means it will add on to the accuracy of the model, right? If it's a 2 star or 2 asterisk, that means your model is 99% confident that your particular independent variable is significant to the model, as in it will contribute to the accuracy of the model. The prediction of the value will be more accurate, right? If it's 1 star or 1 asterisk, that means it's 95% confident. And if it's a dot, if it's a simple dot, it means it is 90% confident, right? So if you look into our data, so our constant is obviously significant, right? Because it's a constant. Then we have the beta values. So this particular value, that is the GLU, is significant, right? And our BMI is significant. Our PED is significant. And the rest of the values it says are not significant. So basically what we are doing over here is basically we are optimizing our model, right? So now if this record is not significant, you cannot straight away remove this record. All right, there are other things that you have to see. Now what are those things? Let's see that. So there are 2 more things over here, 3 more things actually. One is called the null deviance, then we have the residual deviance, and then you have the AIC. All right, so what is null deviance? Null deviance is basically the deviance that you get from the actual value of your data set. So if I'm saying I'm passing these many values and this is the outcome of this. So my particular model is 311 units deviant when it is null. So what is the meaning of null? Null means when you're not using any of your independent variable, you're only using the intercept, this constant. Or if you go by the equation, when you're only using the beta naught and not the beta 1x1 and the beta 2x2 and the beta 3x3, how much is the value that you'll be getting, right? How much your model is going to be deviant from the actual value. So it is 311 units. When we talk about the residual deviance, so your residual deviance is basically when you include your independent variables in your model. So when you include your independent variables, this deviance is actually coming down to a smaller number, right? Which is obviously the fact, because whenever you're using the independent variables, you are making the accuracy of your model more correct, all right? So this value comes down at 229.35 from 311.15, which is correct. Now the third value is AIC, right? So this value should be as minimum as possible. So this is helpful then when you are actually removing the not necessary independent variables from this data set, right? So now we will be optimizing our model. Now how will we optimize our model is like this. We know that this particular or the number of pregnancies is not a significant independent variable, as in it is not contributing to our model according to its calculations. R is telling us that even BP is not a significant variable. Skin, that is the skin fold test, is also not a significant variable. And according to R, age is also not a significant variable. Now how can we double check this? Is like this. So we will basically remove one by one the independent variables and we'll check what are the difference in the values of this. So basically your residual deviance should not increase and your AIC should decrease. So if both of them is true, then your variable removal is right. So let's do that. So let's call our model function and remove age from it. So if we remove age and then we call the summary of the model, let's see what different values we get. All right. So my residual deviance value was 229.35 before, and now it has increased to 231.57, which is not right, right? Also, my AIC value had to be reduced if I'm removing a variable, right? But it was 245.35 here, and it has actually increased to 245.57. That means age is a significant variable, hence it cannot be removed, right? So this is the conclusion that we get by interpreting the data. The next not significant variable is BP. So let's take BP from here, right? So BP is again not significant. Let's try and remove BP. So if we remove BP, let's see what are the changes that we get. Let's now get the summary of the model. Alright, so if I remove BP, earlier my residual deviance value was 229.35 and my AIC value was 245.35. When I remove BP, my AIC value is going down, but my residual deviance value has gone up. It has gone up by 1 unit. It is 230.33 here, and over here if you compare it, it is 229.35. So again, I don't think BP can be considered to be removed, and hence will not go ahead with it. We will not remove BP. Let's try the other value. So what are we left with? So our npreg is not significant now. We have tried BP. We have not tried skin as of now, right? So let's try the number of pregnancies now. So we'll be removing minus npreg from our model, and let us get the summary of the model now. All right. So as you can see, my value was 229 over here. It's 231. It's a change. It's a significant change. And my AIC value is also the same if I remove npreg from here. So we'll not be removing npreg as well. Okay, wow. Let's try the last variable, which is skin. So let us enter skin. So we'll be removing skin from the model now. Let's get the summary. Okay, so before my value of AIC was 245 point something, so it has reduced. Awesome. And my residual deviance was 229.35, and now I'm getting 229.61. Not a significant change, and my AIC value has also reduced. So this can be considered, right? So we can remove the skin parameter or the skin variable from here, and hence get a value which is like this, right? So we will go ahead with this. We will remove the skin variable, and our model seems to be now optimized. All right, so I've removed the insignificant part now, right? So let us go back to our slide. Right, so let's move ahead. So as you can see, the insignificant field was skin, which has now been removed. So what does null deviance mean? I told you guys how well the response variable is predicted by a model when it includes only the intercept, which is this. And what does residual deviance mean? It means how well the response variable is predicted with the inclusion of independent variables. So this is what we have learned, right? Moving ahead, now let's predict values out of our testing data set, right? And check out the accuracy for our model. So what we'll be doing now is we will be predicting the values in the model using our testing data set, all right? So let's pass this, and let us check what this variable has in store for us. So if I type in RES over here, it gives me these values. Alright, so these values are all probabilities, as you can see, 0.0451, 0.628, 0.200, 0.36, and so on. So this is the testing data set that has been predicted, and these probabilities have now been attached over here, right? So the patient number 2 has a probability of 0.0451 of being diabetic, all right? So if we were to check this, let's quickly check this for our patient number 2. So if it's 0.051 for our patient number 2, that means it is close to 0, right? So he should not be diabetic. So let's check out the real values. So for the second patient, our type is 0, alright? So our model is predicting right. The values are right in a model. So patient number 2, the type, if he were to have diabetes, it would have been 0. And my model also says that he has a 0.04% chance of having diabetes. Alright, so far so good that my model has been corrected right. Let's check one more value. So for patient number 6, my probability is 0.628, alright? So that is greater than 0.5. That means he should be diabetic, right? So if we check that, so yes, my patient is diabetic. So my model is correcting right, right? It is predicting correct values. Now how will you check the accuracy for your model, right? So we will be checking the accuracy of the model by this. So now we have passed this command as of now. We have predicted the model using the testing data set, and we have typed and type is equal to response. So response means we want to get an answer. We want to get a probability out of our predict model or out of our predict function, right? So we will be writing predict, and in our predict function we will be passing the model that it has to refer and predict a value from. We'll be passing the data set, the values that we'll be taking from the data set and predicting the value, and the type of that answer should be response, right? And it will be storing all of this in the res variable, right? So we saw the res variable, it has all the probabilities. The next step is creating a confusion matrix. Now what is a confusion matrix? It is actually very simple once you understand it. Alright, it might be a little complex to understand, so let be a little careful over here when I'm telling you, right? So in my confusion matrix is something like this. This is my actual value and this is my predicted value. Alright, so actual values is something which is there in my data set, and my predicted value is something which has been predicted by the model. Alright, so in my actual value, my data set had values which was 0 and 1. Alright, so in the type, my type could be either 0 and 1, right? So my actual value was either 0 or 1. So, and my predicted value has values which has either false or true. So false means he is not diabetic, that is 0, and true means he's diabetic, that means 1. Alright, so my confusion matrix is something like this. So let me draw something here. This is my matrix. Alright, so when my value was 0 and my predicted value was also false, that means when my patient was not diabetic and the model also predicted that my patient is not diabetic, this scene or this scenario was 47 times found in my data set. Alright, which means 47 times in my data set it has occurred that my actual value was 0 and my predicted value was also 0, right? And 13 times it has occurred that my actual value was 0, that my patient was not diabetic, but my model predicted that my patient is actually diabetic. Alright, so this is the error. This is 13 times it has occurred. Again, for the value 1, for the patients who were diabetic, right? So my model predicted that the patients are not diabetic and he was actually diabetic in the actual value. So in my model, the patient was diabetic, but my model predicted that he is not diabetic. This has occurred 9 times in my model, right? And for the data wherein my patient was actually diabetic and my model also predicted that he is diabetic has occurred 15 times. Alright, so this is how you can read a confusion matrix. Now if you were to find the accuracy in this case, so if you were to ask me the formula is basically right diagonal. This is the right diagonal, right? So 47 plus 15 divided by every record in the confusion matrix. Now why is this? Let me explain you that. So when my actual value was 0 and my predicted value was also false, 47 is the number that I predicted correctly. Alright, so that is 47. Again, if we were to ask when my actual value was 1 and the predicted value was also true, 15 was the number. So 15 is also correct, right? But when my actual value was 0 and my predicted value was true, that was 13. So this is the error. Similarly, when my actual value was 1 but my predicted value was 0 or false, my value is 9. So this is again the error. So if we were to find the accuracy is correct number of instances over the total instances, right? So the correct number of instances are 47 plus 15 divided by 47 plus 13 plus 9 plus 15, right? So this is what I've done in the next step. So for calculating the accuracy, I've written 47 plus 15 divided by 47 plus 15 plus 13 plus 9, right? So it came out to be 73%. Let's check in our model as well. So we will be passing the data set now, right? So for passing the confusion matrix, this is a syntax. I will explain you the syntax in a minute. Let's see the output first. So I'm assuming my threshold to be 0.5 as of now, all right? So let's predict. So this is my confusion matrix. All right. Now if you see, my actual value was 0 and my predicted value was also 0 has happened 52 times, right? And my actual value was 0 and my predicted value was true, as in my patient was not diabetic, but my model said he is diabetic, it happened only one time in my model, right? So this is the error. Similarly, my actual value was 1 and my model predicted that he is not diabetic, which is very dangerous, right? If you are going through a disease and you go to the doctor and doctor says you're fine, you're actually been given a wrong consultation, which could be harmful or it could cost you your life as well, right? So this is a very sensitive number. This should be the minimum, right? Because it is okay if you are not diabetic and the doctor says you turned out to be diabetic, that is okay because you are actually fine. But in this case, you actually have diabetes, but your doctor is saying you don't have diabetes and you might end up costing your life as well, because this is diabetes. What if this case or this model was for cancer, right? You had cancer and the doctor said you're fine, it could have been a huge catastrophe, right? So like I said, now let's calculate the accuracy for our model, which has come out from a confusion matrix. So it is 52 plus 18 divided by 52 plus 18 plus 12 plus 1. All right. So my accuracy now comes out to be 84%, which is a very good number, guys. All right. So my accuracy is 84%. So we have optimized our model correctly and we have got the accuracy at 84.3. Now we have assumed that my threshold is to be 0.5. Now how can we be so sure about the threshold, right? What if I increase my threshold and my accuracy actually increases? And also this number has to be reduced, right? This number should be the minimum. What if this number can further go down? All right. So for that, we need to have the correct threshold. Now, one way of doing this is by actually doing the hidden trial method, by trying each and every threshold and seeing what are the effects that we get in a model, or what are the effects on the accuracy of the model, or what is the effect on the confusion matrix. But is there any other way through which we can find the threshold? Let's think about that. All right, so don't think too much. R actually has a method called the ROC curve, which is used to calculate the threshold in your model. All right, so let's see how that thing is done. So first you have to put in the predicted values. The predicted values should be from the training data set, because you're basically calculating the threshold from the training data set so that they can be applied to whatever value you'll be passing to your model. All right, so your threshold will be collected from your testing data set. So let us do that. So our RES should have the predicted values from our testing data set. So let us change our RES. All right, so this is our RES, guys. So let us change this to training data set. All right, let's run this command. Okay, now next is running the ROC command. So the first step towards creating your ROC curve is actually including your library in your environment. So first you will include the library ROCR in your environment, and then you will be passing your next line of code. So you have stored the predictive values for the training dataset in the RES variable. You also imported the library for the ROCR package. The next step is define the ROCR prediction and the ROCR performance. All right. So prediction and performance are parameters that the curve uses to actually plot the graph. So you have to specify them. Inside the prediction, you have to specify the predicted result set, comma, the result set that is actually there, right? So RES, which is predicted, and this is the actual data set. So this is compared and it is stored in ROCR pred. All right. After that, you check the performance. So in this, you are actually passing the ROCR pred. So you will see how good your prediction is, and then you will plot it against TPR and FPR. So TPR is basically the true positive rate, and FPR is basically the false positive rate, right? So you will be specifying the TPR, FPR, and you will be checking the performance using the prediction that you'll be doing today. All right, so let's do that. So we have included the library. So let's pass on these two commands, run them. Alright, so my ROCRPRED and my ROCRPerf have been saved, have been executed. Our next step is plotting the graph, alright? So for plotting the graph, I will be plotting ROCRPref, right? The performance curve I'll be plotting, and I can also color the graph. So I have set colorize equal to true. So this basically colors my graph in a way so that when the values are changing, the graph's color is also changing. And then I want the cutoffs to be printed in the graph as well. So this basically means that whatever cutoffs experience a change will be printed so that it becomes easier for me to choose the threshold. Right, so once you execute this command, this is how your curve will look. This is what is a graph that you'll be getting. So let's pass this command. Let us plot the graph for ROCR. All right, so this is the graph that you get. So as you can see now, how will you interpret this graph is something like this. This x-axis is basically the false positive rate. So this should be the minimum, and this is the true positive rate, and this should be the maximum. All right, so if you go by this graph, as you can see, between zero point 0.3 and 0.2 there is a lot of gap for the false positive rate. So if I give 0.2 as my threshold, I'll be actually going towards the false positive rate, and my model will go towards lesser accuracy. But my 0.3 is going towards higher true positive rate. At the same time, it has the least false positive rate, right? If you compare it to 0.5, 0.5 actually had a less true positive rate. Though it had a less false positive rate as well, but it had a true positive rate which was less as well. Now, what does this mean? This means that this value, which was dangerous, because if I was a cancer patient and the doctor told me that I'm okay, it would have been very dangerous for me, right? So we have to reduce this value. And this value can be reduced by increasing the true positive rate, right? So, but this might also cost you the accuracy of the model. But in that scene, our aim is actually to serve the humankind, right? So your model should be able to predict the right values and the correct right values. It is okay if a model predicts that I am diabetic even if I'm not, right? But if I'm diabetic and it tells me that I'm not diabetic, that actually is a dangerous thing, and that thing should not be there. That thing should be more accurate, all right? And that is what we are trying to solve here. So it depends on your use case, what kind of threshold you will choose. Now you may have some other use case wherein this particular value does not matter, right? So for in that case, you will choose your preferable threshold. But in our case, which is the medical case, wherein you are predicting whether that guy is having a particular kind of disease or not, you have to reduce this particular number, all right? So according to our graph, I should be choosing 0.3 and not 0.2. And if you compare it with zero point 0.4 actually, so zero point 0.4 and zero point 0.3 actually have a very little margin of false positive rate, right? So I'll go with zero point 0.3, all right? Now let us check the threshold 0.3 in a testing data set confusion matrix, all right? And then see what is the difference. So we will copy this and we will paste it here. So our result should be for the testing data set, predicted values, right? And then so let me do it for 0.5 again, and then we will be able to compare our confusion matrices. So this is testing. All right, so this is the confusion matrix for my threshold 0.5 for my testing data set, right? Now let us do it for 0.3. Okay, so as you can see, my value for this value, which is when my patient was diagnosed wrong in the sense that he had the disease and he was told that he does not have the disease, has been reduced to 6 by changing our threshold to zero point 0.3. At the same time, our accuracy I think has also gone down. Let's check. So for the first confusion matrix, let me get the accuracy. So it is basically 52 plus 18 divided by 52 plus 18 plus 12 plus 1, right? So it is 84.33. All right, now let us check our accuracy for zero point 0.3 threshold. So it is 48 plus 5 and then 48 plus 5 plus 6 and plus 24. Sorry, this is 48 plus 24. All right. So let's check. Awesome. So my accuracy has actually been increased to 86.7%. And at the same time, my this value, that is my true negative value, has also gone down. All right. So this has been a very fruitful exercise wherein we found out that whenever our threshold is zero point 0.3, we will get 86% accuracy, and at the same time our model has improved because now my true negatives have been reduced. So if my patient is diabetic, then the chances that he will be diagnosed wrong has gone down, right? So any doubt in this part, guys, that we have reduced the true negative part, that is from 12 we have gone down to 6. And at the same time, usually what happens is when you'll be solving other data sets, when you bring down this value, your accuracy might come down a little bit. But since this is more important, you suffice or you let go the accuracy and you stick to this number. But in our case, our accuracy has actually gone up, which is a good sign. All right, so we have 86% accuracy, which is tremendous for our model. And we have also brought down our number of true negatives. So awesome, guys. So my accuracy for my testing data set is 86%, which is awesome, guys. Now let me recap what we did. We got to learn how you can create a model, right? And then we divided our data set into testing and training. Then we trained our model using the training data set, and we tested our model using the testing data set, right? When we tested our model using the testing data set, using the 0.5 threshold, we got an accuracy of 84.33%, all right? Then we were not sure whether that threshold value is right or wrong. So we went to the ROCR curve, and also we wanted to reduce the values of true negatives, right? So we went to the ROCR curve. We saw that 0.3 is an optimum value for the true positive rate and the false positive rate. And we put the value as 0.3 in our data set, right? And then we plotted, and we then came up with accuracy, and our accuracy actually improved to 86.74%. And at the same time, we also reduced the true negatives. All right. So this is what we have done until now. So this has been fruitful. All right. So we are done with the demo, guys. Any doubts in the demo part? You can come up with the question right now and I shall explain it to you. All right. No doubts. Okay, let's move on to the next part of today's session, which are the use cases. So in 2005, we had this use case wherein we had to predict which areas in Africa were breeding grounds for malaria so that we can provide their help. And what we had was a limited set of values for a small part of Africa wherein malaria was actually present, right? Now, along with geographic information system, what we did was we took the topography of the areas where malaria was there, right? So malaria is basically is there where there are dense vegetation, right? Where there is a lot of water. So there are a lot of mosquitoes over there, and hence you have malaria felt over there. So what we did was, using the geographic information system, we calculated the topographies of these areas where malaria was more. And at the same time, we also had areas where malaria was less, and we also had the topography for those. Now this data was used to create a model, right? And then we had to predict. Now we had topographies for the rest of the areas, right? So let's say if we have the topography for this area, so this area was then fed to the model, and then the model predicted whether this area will have malaria or not. And based on the probabilities, we came up with a plan that which area should be given more care first, right? So if this is orange, and as you can see this is yellow, so this has more probability of being malaria prone, right? So our help could first go to this area and then maybe this area, because this area might need more help from us, right? So this is how logistic regression was used. We fed the geographic information systems data, and we came up with a model, and then that model was used to predict the other areas of Africa wherein malaria could be there. All right. So this is how we used our logistic regression in this use case. Our next use case is used in case of marketing. So Basically, it is used in the marketing research firms wherein you have to know your customer. So when you have to predict whether your customer will buy this product or not, so that can be done using logistic regression. So logistic analysis is used by marketers to assess the scope of customers' acceptance of a product, right? Like in our company, if we come up with a product, say we come up with a shaving gel, right? And we see the past market trends, that what product has been more successful, what kind of product has been more successful when it comes to the shaving creams. We can create a model and then we can feed our values, our new features into that model, and then that model can predict whether our product can be successful or not. So it is used by the marketing research firms, and basically it is also used in targeting ads. So basically whether what kind of data should be fed to you, right? So say if I want to predict whether you will buy a pen drive or not, right? So that will depend based on your search history. Whether have you searched for a pen drive in the recent days? Were you looking for a pen drive on, say, Amazon or something like that? And based on those values, my model will predict whether you will buy a pen drive or not. So based on all these information, marketing research firms, they come up with data and they sell it to companies which actually need that kind of data, right? So if I'm a company, say I'm an e-commerce company, right? And I need to know what kind of products I should upload or I should display in my website so that more customers are there. I can do that using logistic regression. I can actually ask the model which product would be more successful and hence keep that product on my e-commerce catalog. All right. So these are the two use cases that we just discussed. Okay guys, so with this we have come to the end of our session for today. We are over with logistic regression. Any doubts in any other scenes that we discussed today? All right, so Dinesh is saying thank you, nice session. You're welcome, Dinesh. Okay, so since none of you have any doubts, let me wrap up this session for today then. So let me recap what all we did in today's session. So first, we looked at the 5 questions which can be asked in data science. And according to that, we got to know which algorithms could be applied. And then we discussed what is regression. After that, we moved on to the part that logistic regression, what is logistic regression and why it is used. And then we saw what is the working of logistic regression using an example. After that, we moved to the part wherein we did a demo on diabetes use case and we applied logistic regression and we came up with a model which could predict whether you are diabetic or not based on specific values. And in the end, we saw use cases wherein logistic regression has actually been applied, right? So guys, this is what we did today. Any doubt in any other part that we have discussed till now? Again, I'm asking you, I can repeat it all over again. I have no issues. All right, so since none of you have any more doubts, so let's wrap up today's session. So thank you guys for attending today's session. It was a pleasure to teach you guys and I hope you learned something new today. Assignments have been uploaded to your LMS. I expect you guys to solve those assignments and come in our next session. Also, I would expect you guys, since this was a little complex topic, I expect you guys to go through the recording again in your LMS, right? And come more prepared in the next session because our next session is going to be on a topic which is polynomial regression and it is actually kind of based on logistic regression as well, right? So be prepared with logistic regression so that it becomes easier for you to understand what polynomial regression is, all right? So guys, this brings us to the end of our session. So thank you everyone. See you in the next session. Goodbye.
I hope you enjoyed listening to this video. Please be kind enough to like it and you can comment any of your doubts and queries and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!